So, you want to build an induction coil, eh? Well, let me begin. There are a number of items on this board which are integral to the operation of the device. Namely, two MOSFETs. These commute electricity through the coil in the tank, and they cause an oscillation to occur between the capacitor and the dual winding over here. Now, electricity flows through here, minimum of 15 volts, through this inductor here, and through the center tap. It goes around each of the coils, through each of the MOSFETs, and out through the ground. Now, you may be wondering, well, how does this thing oscillate, given that electricity is flowing around through both of the MOSFET gates and out? Wouldn't this just approach a steady state, you might be wondering? And I wouldn't that too. Well, let us examine this a little bit closer. First of all, a couple of things out of the way. These two things here are xenodiodes, set 12-volt xenodiodes. Their purpose is singularly to regulate the voltage at the gates. So, should we see a higher voltage than 12 volts here, these xenodiodes will shunt the voltage, shunt the current through to the ground, thereby limiting the voltage at the gates. Since these MOSFETs, the way they are constructed, you cannot have more than 20 volts difference between the gate and the source. Thus, the 10K resistors here are simply to pull down the MOSFET gates in the event that we approach zero, to ensure that these things go properly off. And the 470 resistors here are to limit the current going through both the Xena and the 10K. Okay. The 200 microhenry inductor here is to prevent the back EMF from destroying your power supply. Quite crucial. Right, now let us proceed to explain how this thing operates. The crucial element here are the diodes. You'll see from either side a diode connected to the opposite side of the coil. Thus, this top rail here has a diode connected to the bottom rail of the inductor tank circuit. And this bottom rail here has a diode connected to the top rail of the inductor tank circuit. Now, imagine we turn this thing on and we have current flowing through the center tap and through each of the MOSFETs. This is a steady state. There's no potential difference between here and here, so how can the capacitor be charged? How can any oscillation happen? Well, as it happens, any minute fluctuations caused by differences in the MOSFETs or the resistors or atmospheric conditions or, whatever may, will cause a potential difference to occur. This will cause the capacitor to be charged ever so slightly. And then what this will also do, because there is now a potential difference, there will be a potential difference between this rail. Let's imagine, for example, that this is charged here positively and this negatively. There will also be a potential difference between this top rail and the bottom rail, which means we will start to draw current away from this gate. This will turn this gate off, which will stop the flow of current here, and therefore it will allow the potential difference to be normalized, and the current will have nowhere to go, so it must flow out of the capacitor and through the induction coil. This then, because of the back EMF of the induction coil, pulls the current in the opposite direction slightly. So what we get set up is a very minute oscillation. So the capacitor charges, pulling this gate off, which then allows current to flow through the coil this way, and it charges this one. And when this one charges, it then pulls this gate off, which then causes the current to flow back through this way. Each time the back EMF contributes to the build-up of voltage. So I hope that was clear, but it's rather complicated. So I'm going to show you an animation which might make that more apparent. But essentially, this is how it happens. What we have is the capacitor charging, and the charging action being set up by a potential difference causes the gate to close, which then causes the capacitance to be discharged through the coil. with a corresponding back EMF that then charges the capacitor in the other way. So this action is commutated by the diodes, and this causes what is known as the zero voltage switching of these MOSFETs, since they go to zero voltage and they turn off in sequence like this. The oscillation of this tank circuit will have a resonant frequency determined by the capacitance and the inductor that is chosen. So we can set the frequency by changing these things. Of course, we often manufacture this using copper coil, and this may be quite difficult to manufacture. Therefore, our inductance is often set. So then we have to modify our capacitor in order to get the frequency we desire for the correct heating of the metal element. Okay, so that's how it works. And let's have a little look at an animation, shall we?
Okay, so I've been depossessed from that Victorian fellow and I'm back to normal. So what I want to show you is a quick animation of how this works. I'm using a tool here called Circuit Simulator, which is from falstad.com. So www.falstad.com/circuit. It's a very nice simulator because it shows the flow of current. I've got this the file for this circuit from a YouTuber called Doom2 Pro, because he had a simulation of it. Now what you might notice is that it actually says flyback driver. This is because the circuit's identical. We're using a flyback driver circuit, but instead of a secondary coil here being a high voltage generator, our secondary coil will be the thing that we put inside the induction coil. So, you know, the piece of metal that we want to heat, and that'll be like a coil with a single turn, essentially. And how the induction heater works is, when over the primary, so our work coil, when we induce a alternating current of a very high frequency, this obviously sets up a very strong alternating magnetic field, which then induces in the secondary, which will be our workpiece that we put in there, a piece of metal, induces currents. These are called eddy currents, and because everything's trying to move around and there's nowhere for it to go, it generates resistance, as in any piece of wire generates resistance, which causes the workpiece to heat up to a very high temperature. So let's have a quick look at this. So the oscillations are between the capacitor and the secondary. So this is a center tapped coil here, and this driver is known as a Mazzilli driver, after the guy that, you know, popularized it. But there's another circuit called a Royer oscillator upon which it is based, which dates back to 1954. So let me reset this simulation, and I've got a plot down here which is going to show the voltage over the capacitor. And okay, so now it's running, and you can see the oscillation, so going back and forth to both plates of the capacitor are charging and discharging. And you can see at the bottom here on the graph that the system reaches a kind of steady state, or a steady oscillating state, where the oscillations are fixed. They actually build up, if you look at the beginning, they build up from nothing until they reach the peak, and then they stop at that peak to peak, and they remain stable like that. Now the reason that they build up is because every time you get a discharge, if I slow it down and reset it, there we go, is because when this is charging up, and I've slowed it down so you can see that the capacitor is discharging, and this initial potential difference to charge the capacitor can be very small to begin with, but it discharges across the inductor, which means that when the second plate is then charged and we discharge in the opposite direction, you've actually got a collapse of a magnetic field here, so you get the back EMF, which then causes an increase of voltage when it's charging up the other way. So each time the oscillations occur, you have the additive effect of the back EMF from the coil, which then causes the voltage to increase. That's why we see a voltage increase as the oscillations on go until we reach the resonant frequency of the capacitor and the coil, which is just we're just about reaching the first swing of our oscillation here. if I speed it up, we'll be going back the other way. But yeah, just that's really the key there, to the voltage build-up in the tank circuit, is that we're swinging through an inductor, so you get back EMF adding to the charge. And now also what you can see in this animation is that if I have a look at the gate, this is called zero voltage switching, which means that the gates really go all the way off. Okay, it struggles a little bit to. You can see here on the gate that we're actually off. We've got off periods here. Now, with this particular inductor and this capacitor, we're about 65 kilohertz. We want it to be faster than that for most heating, because the heating occurs via a skin effect, and for different frequencies are suitable for different metals, and depending on the size of metal you want to choose different frequencies, so it's good to be able to change out your capacitor to get the matching correct. Right, so the final thing I wanted to say is every time we switch, the switching causes this via these diodes, these two diodes, that's what actually pulls the gates down and turns them off. And so if you look at the gates, you'll see them alternately going green because they're alternately on and off, because each one, this corresponds with the flow of, with the changing potential difference between these two lines, because that causes alternately each of these diodes to pull off each of those gates alternately, and that's how you get the switching effect. Alright, well, I hope that made things a bit clearer, but you know, you can look up this guide, download the simulator and play around with this yourself, and it's a very simple oscillator, and it's probably the easiest induction heater to make, and that's why I chose it to do. Alright, I'm going to tell you how I built mine. So the components I used, this is a IRFP 150N MOSFET, and on here these are heat sinks I got off a very large uninterruptible power supply, a very large one, and so this will keep these nice and cool. These will get hot. Now the IRFP 150N has a voltage, a maximum tolerable voltage between the drain and the source of 100 volts. That means that we cannot really use an input power of more than something like 40 volts. This is because the way that the induction coil, the back EMF of the induction coil causes the resonant voltage to be a lot higher than your supply voltage. It's approximately pi times the supply voltage. I've got 24 volt supply, and so yeah, you'd expect that to be something like 70 volts around that, and that's pretty much what it looks like from the oscilloscope. So there's only 30 volts to play with there. If you want to drive it with a high voltage, then you're probably going to need a bigger MOSFET. Another important feature of the MOSFET is make sure you get one with a low on resistance. I guess that's pretty obvious. You don't want it to heat up when it's on, so you want it to look like a closed circuit when it's on. The other components here are these are the diodes, the two diodes. The switching diodes, the ones that feed the signal back to either side of the work coil and switch it on and off. And in this particular case, I pulled off the UPS one's DS145-08A. They've got a maximum reverse voltage of 800 volts they can tolerate, and quite a high current. By the way, the MOSFETs can have a forward current of 44 amps, so they're pretty beefy things. The Zener diodes here, 12 volt Zener diodes, are just 1 watt. They don't pass a lot of current. The 10Ks here are 2 watt resistors, and the 470s here are 2 watt resistors as well. Looking at the capacitor bank, now the capacitor bank is going to be switching as fast as your resonant circuit is switching. So this means it has to be able to tolerate high frequency switching, otherwise it does get very hot. And it will get hot. This will heat up quite a lot. In my case, it won't, because these are 850 volt capacitors designed for a rectifier, so they're designed for high frequency switching. Each of these is 1 microfarad each, and in order to ensure that they do not get hot, I've got 4 of them in series to give a capacitance of 1/4 of a microfarad, and then put that configuration back to back with another 4 to give approximately half a microfarad, or 500 nanofarads. Now that, coupled with the coil, this is a Rob Special coil, rectangular coil. We've got a special purpose in mind for this one, and this has an inductance of around 3 microhenries. Now if you do the calculations, it's 1/2 pi to the square root of the inductance times the capacitance, and the calculations say it's around 136 kilohertz, but in practice this is actually oscillating at 175 kilohertz. So because probably I haven't measured the inductance properly, and the capacitance isn't exactly as I imagine it to be, and so on, and in reality things in the physical world tend to not behave ideally. So that's the tank and the inductor. We need to power this thing as well, of course, so I'll give you a quick look at what power supply I'm using here. Now we've got this computer place, and they get these by the ton, literally by the ton, and so we managed to get these pretty cheap off them. And these are old server power supplies. This model is a 7000-814-0000, and this model is an NPS 700AB. These are 12 volt power supplies. They're actually both the same. They've both got a rated current at 12 volts of 57.3 amps. Now, the only difference between this one and this one is this one has a little voltage adjustment, so a little trim pot in there, so you can change the output voltage if you want. Now I've wired these up in series to give me 24 volts. The way to wire them up in series, well, what you need to do is the DC output and the AC input are both grounded to the case, which means if you take the DC output from here and just try to wire it in series like you would with a couple of batteries, you're in essence shorting the DC output directly to ground, since they're all tied together. So the way to put them in series is to open this up and remove the DC grounding, which means that when you put the DC positive into here in series, you're not shorting it to ground, and therefore you actually get the 24 volts you want. The way I did that, I don't know if you can see here, I just took the screws out and bent away the chassis grounding attachments, and that worked just fine and dandy, actually. I'm going to clean this wiring up. I know it's a mess. The only other thing you'll note here is I've put a couple of rather crude filters on the back to stop me putting my fingers in there and getting them chopped off in those powerful fans. Alright, oh, one final thing I forgot to mention, a couple of things. We've got the induction coil. This is a filter induction coil that stops back EMF from wrecking your power supplies and from power leaking away, essentially, away from the tank. And just got that off the UPS again. I measured it, it had an inductance of 184 microhenries. The final piece here is just around here, is on the back, I think you'll notice, but I've got a fan over there which again was off the UPS, and that's a 24 volt DC fan, so that's blowing air across the MOSFETs to stop them from overheating. So that is the complete setup there, and this makes a hell of a lot of noise when you plug it in, but it does work. Right, well, let's fire this thing up and have a look what it can do. So you can hear the thing whirring away And you can see there that it's glowing quite nicely now. I don't want to go too close in case the magnetic field does something to the camera. You may be wondering why there is a spoon inside the induction coil. Do you recall the video where Steve copper plated a stainless steel spoon and Rob subsequently soldered a wire to it? Well, that spoon didn't like it. It didn't like to be burned like that. And it set upon us its army of spoons. I captured one, and now I'm going to interrogate it to make it yield its secrets. So let us see. Will it reveal its secrets or not?
Throw the switch, Igor! Throw the switch!
It melts! So there you go, you've seen an induction heater melt a few things. I've explained how to make it. Hopefully you can make your own and show us. That'd be really interesting. I think the next stage for this one is more power. It needs more power! Everything needs more power. Alright, thanks for watching. Cheers.